In the previous weeks, we have looked at the R format and I format instructions. Each format has a different bit pattern that when the instruction is being assembled, the instruction is converted to that bit pattern. And then the processor can look at that pattern and understand that what does it mean basically, and decode each parts of that instruction. So we said that the R formats had a general they generally have two registers. So example of that was, for example, add followed by two register. And then we had the I format that they had the immediate value. So for example, if you're adding a number, so add I, for example, or some of the branch instructions also. So the most obvious thing to know that you're dealing with the I format is that it has usually at least one register up to a maximum of two registers, and it usually has a number. So that was our I format, and this number that we had here was 16 bits. So in this lecture, we are going to look at the J format, and that is the last format that we're going to be looking at. So basically, the J format, there are a few instructions, but the major difference is that it doesn't have any register, and so that means that because it doesn't have a register, it has more space for a number, and that number is 26-bit immediate value. So let's go to the slides and look at this. Okay, so here are some instructions that we have seen before in when we are doing the coding part. So one is a J. So you could do jump and you're specifying a label. And similarly, we had jump and link, which was mostly used for functions. So you have the jump and link and a label again, but this time this label was representing a function, and basically the code would execute at that location, and then you had something like jump register to go back to your code to execute line after this one. So both of these are example of a J format. So you see that they have only one label, so they don't have any register, and that gives more space for this number that they're gonna basically store in that 32 bits. So this is the pattern. We have total of 32 bits, and out of that 6 bits, it's going to represent the instruction itself. So that you can think of it as like an ID or identifier for this instruction. So this is going to get a number, and that's going to be represented into these 6 bits. And then the total was 32 bits. And that means that we're going to have 26 bits left out of that total of 32 bits. And that 32 bit going to be any number that we want to represent. So in this case, is the label that's going to be converted to this number. So how does this work? We know that memory addresses. So if you had a jump, so for example, you had jump loop, we know that this is a memory address, and this memory address is 32 bits. However, here we have only 26 bits. So how we gonna construct that 32 bits is we're gonna get 4 bits. So this last 4 bit of the current address gonna be basically the starting of this 32 bits address. So we're gonna basically get the 4 most significant bits, So that's going to be 4 of the current line that you have this instruction on. So you're going to get that 4 bits here. And then you have 26 bits from the I. So that's from the current instruction, the address of the current instruction. So this one is the I. So that's the value that you have here. That's 26 bit. And then we add 2 zeros to that, and then that is 0, 0, which is 2. So if you add this, you're gonna get 32. So that means basically you construct a 32-bit number that is going to represent an address for this jump or jump and link. So let's look at this notation here. This notation of OR operator is actually concat. So we are just joining these numbers. And this is the bits. So when I'm putting here 28 to 31, that means bit number 28. So this PC is the current line or program counter. So that means bit 28, 29, 30, and 31. So that's this notation here. And similarly here, this one, it basically means bit 0 to 25. And we know that this is 26 bits only. So that's basically all the bits from that number. And this one means 2 zeros. So it's not very conventional here. And here is saying the same thing. So the top 4 bits with this number and then 2 zeros. So let's look at the example and it will become more clear. So we are at this location in the code, we are running this line. And the instruction itself is jump there. So that's our instruction. And this line has a label itself, which is not necessarily, but it's more clear now that because this has a label, so that's the label for this line. And the address of that label or the address of this location is basically this number. So we have this number here. So we are going to write this one in a full form. So if you look at it here, this is basically 4 digits. So it's missing 2 digits here. So I have to write it in a full form because I'm going to take 4 bits from that number. So I have to add these zeros. So it has to be 8 digits. So you can pad it by 0 on the left. And what I want to find out is basically this content here, right? So that is what we are going to find out. So let's see how I would make this address from here. So we have, well, actually I have the content and I want to find out the label. So I want to find out the target address, which is calculated down here. So we know that from this pattern here that we have, the 6-bit is the opcode. So 1, 2, 3, 4, 5, 6. So that's the opcode. And that is telling us that this is jump. So the rest of this, continue this is going to be I. Okay. And we said that the processor is going to get 4 bits from the current address. So each digit here, it's actually 4 bits. This is hex, right? So I can, maybe I change this color. So here I'm just gonna get this 1, 0. So that's gonna be as a hex address, and this 0 is coming from here. And that's 4 bits. Here, I'm gonna continue. Every 4 digits is going to be one hex digit. So that's 4. and then another 4, another 4, 1, 2, 3, 4. So 1, 2, 3, 4, 1, 2, 3, 4. So another one is here. So that's 0, 0, 0, 0. 4, 1, 2, 3, 4, 4, and then 1, 2, 3, 4. So then we have a 1, and then 1, 2, 3, 4. We have basically this number 0, 1, 0, 0, which is a number 4. And then I have 1, 0. But if you remember from here, we have to add 2 zeros to this number. So we have to add these 2 zeros. And then if I look at this one, it's actually 1, 0, 0, 0. And that's a number 8. So I can write down this completely 0, 0, 0. So that's 4 zeros. And then from here, 0, 1, 4, 8. So that's basically the address that this, if you are looking at this, the address that we are going to jump. So address of there is actually this number. And that's a limitation. There is no good reason that I would say, like ideally, we want to store that whole 32 bits here. So if this there was this address, ideally I would store this whole thing in my space that I have here. But unfortunately, the whole thing is 32 bits and 6-bit is going for the instruction itself. So I have only 26 bits. And that's why basically there is this limitation that we have to work with to store this address. And these 2 zeros that we are adding, if you remember from the last week lecture, when we are calculating the BTA, so the branch target address, I can rewatch that video, but basically the idea here is that since all the memory addresses are going to be aligned, all of them is going to basically end with 2 zeros. So if you remember, our memory addresses were ending in 0, or 8, or C, and all of these are going to have 2 zeros. So this is zeros, this is 0, 1, 0, 0, 8 is 1, 0, 0, 0, and C is 1, 1, 0, 0. So if you look at this, they all have these 2 zeros. And that's why when we are storing this address into our memory, we can get rid of these 2 zeros. So these last 2 zeros, there is no undo here. These last 2 zeros, because we know that they all gonna end up in that, and we can just add the zeros back when we want to calculate the address.